everyone, I am Voktho. I will be presenting a paper titled Vital Verifying Trojan-Free Physical Layouts through Hardware Reverse Engineering. This paper proposes a framework for post-fabrication layout verification that is both practical and technology agnostic. It addresses an increasingly relevant issue in hardware security, the risk of hardware Trojans introduced during third-party fabrication. As the semiconductor industry becomes more global and distributed, chip design, fabrication, and testing are often handled by different entities. While this is efficient, it also introduces security vulnerabilities. Specifically, the possibility of hardware trojans being inserted during the fabrication process has become a major concern. Many exciting detection techniques such as timing analysis or functional testing are ineffective when the Trojan is small or only alters the layout structure. That's where reverse engineering becomes useful. But reverse engineering is typically slow and lacks a rigorous quantitative method for layout validation. This is the gap Vital aims to fill. The authors present Vital a framework that statistically validates whether a reverse engineered IC layout matches its original trusted design. What's important here is that Vital does not require a full netlist extraction, which is usually a bottleneck in reverse engineering. Instead, it compares polygonal shapes between two layouts and evaluates how closely they align. It also accounts for common errors in reverse engineering and fabrication, such as optical distortion or shape deformation. Here is the complete reverse engineering flow overview. Before Vital can be applied, standard reverse engineering steps are performed. These include depackaging and delayering the IC, scanning each layer using SEM, stitching these images into full layer mosaics, and finally processing the image to extract layout polygons. Vital begins its process after image processing. It does not rely on logic level reconstruction. It works directly on the physical layout, making it broadly applicable and scalable. The threat model considered in this paper is quite realistic. The authors assume that while the design is trusted, fabrication step may be compromised. An attacker at the foundry level could insert subtle layout level changes either to modify chip behavior or to affect parameters like randomness in physical unclonable functions. These changes might not affect functionality in an obvious way, making them hard to detect through traditional testing. Vital targets these kinds of layout-only modification through post-fabrication verification. However, comparing layouts is not straightforward. First, design for manufacturability alters the layout for lithographic optimization. Secondly, manufacturing introduces variability through process like optical proximity correction. Finally, reverse engineering itself adds noise through etching artifacts, misalignment, or SEM distortion. These factors make exact layout matching impossible, so Vital instead uses statistical and feature-based comparison. Let's look at how Vital works. The reverse engineering layout called R and the design layout are aligned using affine transformations. This handles difference in scale, rotation, and shift. Then the framework computes three polygon level features. First one is the centroid distance between polygons, then aspect ratio difference, and the last one is area overlap ratio. The classification metrics are true positives, false positives, false negatives. From this, the framework calculates precision, recall, and F1's code to assess layout similarity. This is the algorithm how Vital works. Vital operates tile by tile and performs the following steps. Extract polygons from reverse engineering and design layouts. Use the above three features to match pairs. Apply median absolute deviation to remove outliers. Calculate the average shift and realign the layout. Rematch and refine using DFM specific thresholds. The method is non-ML interpretable and runs in quadratic time per tile, which is acceptable given its precision. To validate Vital, the author tested it on a 14nm CMOS chip with 7 metal layers. They focused on the first 3 layers, M1, M2, M3, since they are the most dense and error prone. The reverse engineering process involved 4nm resolution SEM images, image stitching, segmentation. Despite imperfections in delayering and noise, the framework performed consistently. Now the results. Without any tuning, the F1 scores for the 3 layers range from 92% to 97%. When the authors applied the FM specific thresholds, the scores improved further, reaching up to 99.7% for M3. They found that most errors in M1 were false positives due to delayering artifacts, while M2 had more false negatives. On average, layout distortions were under 20nm and the tool processed each tile in around 5 minutes. This means that verifying an entire 1mm IC could take about 12 days, but it's highly parallelizable. In summary, Vital offers a reproducible, scalable method to verify the physical integrity of IC layouts without needing to reconstruct logic or simulate functionality. It reduces manual reverse engineering efforts significantly and could also be extended to other domains like PCBs or 3D ICs. The authors suggest future work on first one is handling non-layout Trojans such as dopant level changes. Second one is optimizing reverse engineering flows for sub 10nm nodes, and last one is integrating Vital into broader reverse engineering toolchains for trust validation. Thank you everyone for your attention. This paper offers a great balance between theory and practical application, and I am happy to discuss it further or take any questions.